We mentioned that there are two issues, two enhancements, therefore, will provide to this matrix H. The first one goes back to the problem I just briefly alluded to, that what if a node, say node 4 here, does not point to any other nodes? It's got in degree of 3, but out degree of 0. So O4 is 0. Then what? Well, you can't divide by 0, and this presents a conceptual and mathematical challenge. For example, in this 4-node small graph, we can write down the H matrix 4 by 4 very easily. The first node points to the fourth node only, so it's 0, 0, 0, 1. The second node points to nodes 1, 3, and 4, so out degree is 3. And on columns 1, 3, and 4, we write down 1 over 3, 1 over 3, 1 over 3. No self loop, that's 0. Node 3 is 1 over 3, 1 over 3, 0, 1 over 3. So far, so good. Node 4, that's the problematic one. It's all 0. So if we solve the linear equation associated with this pi transpose equals pi transpose H, that means we have to solve the following equations. 1 over 3 times pi 2 plus pi 3 equals pi 1. Okay? And that's just because this is the first column of matrix H. And then we have 1 over 3 pi 3 equals pi 2, 1 over 3 pi 2 equals pi 3, and pi 1 plus 1 over 3 pi 2 plus pi 3 equals pi 4. If you look at this system of 4 linear equations, the only solution is that all pi's are 0. Okay, so how can we solve this dangling node problem? We refer to these nodes with no out degrees, or out degree being 0, as dangling nodes. One possible solution is to say, well, since you don't point to any other nodes, I will assume that you point to all nodes. I will force you through a mandatory score spreading. You have to spread your importance score, and since you don't tell me which ones you point to, I'm going to say you point to all nodes. Okay? Either all the n-1 nodes, or for simplicity, let's say all the n nodes, including yourself, with a self loop. For example, in the last graph here, instead of this 0, 0, 0, 0, we'll say it must be 1/4, 1/4, 1/4, 1/4. Now here's a shorthand notation to denote this action of forced importance score spreading to all the nodes. What we saw is that we basically say that there is 1 over 4 times 1, 1, 1, 1. Okay? This is a vector of 1s. So we write it as a boldface 1, a vector 1. Since by convention of this research field, I have to flip it over, so this is a row vector. Okay? So it's 1 over n, that's 1/4 here, times a row vector of all the 1s. Okay? That's what we want to use. But only for the dangling nodes. So how we have to identify the dangling nodes? In this case, the dangling node with a binary indicator is the last one, it's the 4th node. So we write down 1 here in a 4 by 1 vector. It's the indicator of all the dangling nodes. If nodes 1, 2, and 3 are not dangling nodes, we just write down 0. If it is dangling node, we write down 1. And now we can look at an outer product between this column vector and this row vector. Okay, usually when we write down two vectors multiplying A transpose B, we mean inner product. Okay, so this column vector flipped, therefore it's 1 by n, and B is n by 1, a column vector. So the inner product is a scalar, 1 by 1. But in this case, we're talking about a column vector producting with a row vector, not the other way around. So we actually end up with a 4 by 4 matrix. It's a little funny operation, but soon you'll get used to this shorthand notation. In this 4 by 4 matrix, the first entry is simply this times this. So that 0 times 1 was still 0. And then you can see that this whole thing would be 0. Similarly, the second row is all 0. Third row all 0. That's because in this outer product, the indicator vector's first 3 entries are all 0, so it doesn't matter what you have over there. The last one is 1 times 1/4, 1 times 1/4, and so on. So you got exactly what you want. Again, this is just a shorthand matrix notation. And we call this indicator function vector W. This vector is just 1. So we have W multiply 1 transpose. And don't forget to normalize by the number of web pages, 1 over n. In other words, we're adding to the H matrix another matrix, 1 over n scalar times W indicator function and 1 transpose. Okay, just to add an arrow to indicate these are vectors. This is the matrix we just talked about. It represents the topology. This is an artificially added matrix. We add to this H. What this addition does is exactly take out all 0 rows and substitute with 1 over n over there. Again, the notation may take a little getting used to, but once that's done, you can easily see what's going on here. Now, H is a very big matrix, and this is also a very big matrix, but this actually is a simple matrix. Forget about the scaling. This is basically saying I'm just putting down a bunch of 1s in certain rows, those rows that are indicated as dangling nodes. And this in particular is called a rank 1 matrix. So we're adding a rank 1 matrix here, which is simply a duplication of 1, 1, 1, 1, 1 vectors, to a very large but sparse matrix H. So sparsity helps, and this low rank also helps, because we can see the structures embedded in this large matrix. We call this new matrix our second matrix. Give it a symbol H hat. And we can model this as so-called random walk on a graph. Why? Because once we've done this, there will be no rows that are all zeros. And by this normalization, we know all the rows will add up to 1. So in the H hat matrix, we can view each row as a probability distribution. It says if you're on a certain page, what's the chance that you'll be going to the other pages? Well, if there are hyperlinks, then you'll be evenly likely go to any of the hyperlinked pages. If there is none, then you'll be evenly likely to just terminate this and hop to any of the pages out there. Now, is this a reasonable model? Is random walk on graph a reasonable model? Well, it depends on what you're trying to model. If you try to model a lot of things, the so-called follows a Markov chain structure, then sometimes it's pretty good. And in the case of navigating on the web, clearly people don't exactly do uniformly picking one of the hyperlinked text. It's a gross simplification, but nonetheless, this random walk on graph following this particular structure represented by H hat matrix turns out to be a reasonable trade-off between realism and tractability.